Let's start this problem by remembering the Arrhenius equation, which states that we have some value k, our rate constant, which equals a e to the negative ea over rt. Okay, so when we're working at different temperatures, we'll remember that this value a doesn't change, but values k and t will change. Ea, r, and little e, of course, are all constant. So let's go ahead and divide these two expressions. So let's take k1 over k2, which is going to be equal to a over a, the a's cancel, e to the negative ea over rt, 1, plus ea over rt2. Okay, so let's work through this now and take the natural log of both sides. So natural logarithm gets us k1 over k2. The e drops away, and we are left with ea, there should be an equal sign in here, equals ea over r, 1 over t2 minus 1 over t1. Now let's go ahead and substitute in our values, and we find that we get an ea of 133.76 kilojoules per mole. That's kilojoules per mole. Okay, next up we're asked to figure out the rate constant at 750 K. So this is just a matter of doing the reverse process now. So we're going to say, okay, we know everything else, but we want to find some K1. So in this case, K1 is going to equal some K2, which we can use as being either of the values that we've started with. So let's take our rate constant at 700 Kelvin, which is 1.3 per molar per second as our rate constant, times e to the negative ea, or rather we can take e to the ea over r, so that's e to the 134 kilojoules per mole over r, times 1 over T2. Remember, T2 in this case is 700 Kelvin, minus 1 over T1, and T1 in this case is 750 Kelvin. Note that even though we've gone ahead and figured this out, we didn't actually need to calculate A. We could have calculated A after we found EA, but we don't actually need to know that value to figure out the answer to this. So if we go ahead and calculate this out, we get a value of 6.017 per molar per second.